Artificial intelligence has evolved into one of the most significant instruments in the modern world. It recognizes or treats what you want to read, can read your handwriting, and can even drive your automobile. While humans are fairly intelligent and capable of performing a variety of tasks, computers are much better, or at least can be if programmed by people of above average intelligence. The ability to learn and make its own decisions is the key to a useful and powerful AI. How does AI work? Computers need to be told what to do, because they are not sophisticated enough to make their own judgments. So, how can we get them to make their own educated decisions? This is the problem with machine learning. The computer's ability to perform two things is at the heart of the problem. The first point has already been mentioned: it must be able to make its own decisions. The second point is that it must be able to forecast, which a smart AI will be able to achieve. Minimal mistake. But how can we get good machine learning results? Because AI is implemented in so many different ways, it's difficult to give a broad answer to this question. However, like most computer science problems, the solution begins with an algorithm. There are many different machine learning algorithms and protocols that are used in different situations, but to get the best idea of how this will work, we'll focus on one of the most popular and widely used methods. What's called biologically inspired computing. After all living organisms, neural networks are the best thinking decision-making machines around. If you want to build something that thinks, the first and most obvious point of cool is to simulate some kind of brain or information processing machine. They can make different decisions given different information, which is the basis of a neural network. In a neural network, the system takes in the starting information, which simulates a bunch of neurons, and depending on which neurons are stimulated, other neurons are stimulated, and the whole process repeats itself into a final result of contagion. So how do we actually implement something like this? Simple neural networks are made up of systems called perceptual inners, which are a type of artificial neuron that takes in several binary inputs x1, x2, x3, and so on, and uses them to produce an output y simply by adding them together. However, the output itself must also be binary, so how do we deal with it? If the sum of the inputs is larger than or equal to some threshold, we say that y equals 1. If the sum of the inputs is less than the threshold, we say that y equals 0. You can start with the idea of a threshold, but in practice we tend to say the output is equal to 1. If the sum plus some negative number 3 called the bias is greater than or equal to 0, the bias is a representation of how easy it is for the perceptron to output to 1, so there's no difference from the threshold idea. It just keeps everything centered around 0. This is a good start, but it's quite a basic model and doesn't allow much complexity. When it comes to making various selections, the problem is that each input xi has the same weighting. We can build a better system if we assign a unique weighting w to each input. We can then multiply each input by its weighting when we take this up. This allows for different inputs to contribute different amounts and gives the perceptron a sense of importance for each input. Do we have a jacket? Does the weather appear great right now? Does the forecast say it will be nice all day? These three factors may be of varying importance to you. It may matter a lot to you that the weather is nice right now, so you wait. It may matter a little if the forecast says it will be nice all day, so they give it a weighting of 1.5. And it may not matter all that much to you if you have a jacket, so you just give it a weighting of 1. Now all you have to do is set your bias.